Hello math students, this video is lesson 2.3 chopping logs. 2.3 continues from lesson 2.2 where we were looking at transformations of logarithmic functions, so moving the log graph up and down and left and right. Today we're specifically going to look at the vertical transformations. Before we get into those, let's look at this equation right here. I want to know, is this a true equation? In order to figure that out, what I can do is I can just plug in some numbers for x and b. So I'm going to go ahead and say, well, maybe x equals 2, b equals 4. So I'm just choosing two numbers. Doesn't matter what numbers we choose. And I'm going to plug those in for x and b. So I go log base 2 of 2 plus 4. I want to see what is this equal to. Well, we know that 2 plus 4 is 6. So to figure out what log base 2 of 6 is equal to, I can look and say, well, 2 squared is 4. 2 cubed is 8. So 6 is between 2 and 4, which means that log base 2 of 6 has to be somewhere between 2 and 3. So now let's look and see what is log base 2 of 2 plus log base 2 of 4 equal to. Well, I know that 2 to the 1 is equal to 2. 2 squared is equal to 4. So that means that log base 2 of 2 plus log base 2 of 4 is equal to 1 plus 2. So those are my exponents, which is equal to 3. Well, 3 is not the same as a number that's between 2 and 3. So that equation is not true. But there's still something that we can look at, another equation. I'm going to look at the graph of log base 2 of 4x, which is what I have on the right over here. This looks like some of the functions that we did in 2.2. It looks like it could potentially be a vertical transformation of log base 2 of x. So what I'm going to do is I'm going to go ahead and I'm going to sketch log base 2 of x on this graph. So remember, when I'm sketching the graph of a log, I always have my x-intercept at 1. Since it's log base 2, I'm going to look for powers of 2. So log base 2 of 2 is equal to 1. Log base 2 of 4 is equal to 2. Log base 2 of 8 is 3. And then log base 2 of 16 is equal to 4. So when I sketch the log graph, it looks something like this. So this red graph is y equals log base 2 of x. To me, it looks like every single point on the log 2 of x has been shifted up 2. So my equation for this graph, I could say, is y equals log base 2 of x plus 2, or 2 plus log base 2 of x. So this equation right here is the same as the equation that I have up here. Let's see if we can figure out why. First off, are there any times when we can have the same graph with different equations? So in secondary 2, we did a lot with quadratics. So those were our parabolas. We had quadratics that were in standard form. We had quadratics that were in vertex form. And we had quadratics that were in factored form. So these are all different forms of quadratics. So they just, all these three different forms did is they just gave us different information about the graph, but they ended up graphing the exact same thing. So once again, I have this, we were looking at f of x equals log base 2 of 4x. We saw from the graph that another way that I could write this is f of x is equal to 2 plus log base 2 of 4x. I'm sorry, not log base 2 of 4x, just log base 2 of x. So let's look at a few more examples to see if we can figure out maybe why these are the same thing or where we can see the different parts of this equation. So let's look at log base 2 of 8x. I'm going to start by looking at just the graph of log base 2 of x. So once again, I always have an x-intercept at 1, and then I look at powers of 2. So 2, 4, 8, and 16. And then I just go ahead and connect these. And then I notice that I have on here a vertical shift of 3. Everything has been moved up 3. So I can say my equation for this is y equals 3 plus log base 2 of x. If I come over to b, I'm going to do the same thing. I'm going to look at the graph of log base 2 of x. Look at powers of 2 to help me sketch this. And then connect the dots. And then I notice that I have a vertical shift of 4. Everything here has been moved up 4. So the equation that I can write is y equals 4 plus log base 2 of x. I want to figure out how does this 3 relate to my original equation with a 2 and the 8? And how does this 4 relate to my original equation with the 2 and the 16? Well, I noticed that 2 with an exponent of 3 is equal to 8, which means that log base 2 of 8 is equal to 3. So I could rewrite this equation as y equals log base 2 of 8 plus log base 2 of x. Same thing on b. 4 is the exponent that I put on a 2 to get 16. So I could rewrite this as y equals log base 2 of 16 plus log base 2 of x. So once again, all I've done is I've just rewritten this 3 as a log. Log base 2 of 8 equals 3. I've rewritten this 4 as a log because log base 2 of 16 is equal to 4. I could do the same thing with what we had on the previous page. I could say, well, 2 is just equal to log base 2 of 4. And so all I did right here is I rewrote the 2 as a log. To summarize this, I'm saying log base 2 of 4x is equal to log base, or is equal to 2 plus log base 2 of x. But 2 is equal to log base 2 of 4. So I really don't even need this middle section right there. I can just say log base 2 of 4x is equal to log base 2 of 4 plus log base 2 of x. Same thing for log base 2 of 8x. We saw that it was a vertical shift of 3, but 3 is just equal to log base 2 of 8. So I don't even need that middle section there. And then for log base 2 of 16, it was a vertical shift of 4, but 4 is just log base 2 of 16. So I don't even need that. So what we should notice is this, what I have in the parentheses over here, I have split those two numbers up between two different logs. Same thing with 8x, I split those two numbers up between two different logs. 16, split that up between two different logs. So this is an example of what is called the product rule. The product rule tells me if I have two or more things that are multiplied in a single log, I can split that up between that same number of logs. So log base 2 of a times b is the same as log base 2 of a plus log base 2 of b. So let's look at an example of where this works. So I'm going to choose two numbers, maybe a equals 4, b is equal to 8. And I'm going to see, well, what is log base 2 of 4 times 8 equal to? Well, 4 times 8 is equal to 32. Two to the 5 is equal to 32. So log base 2 of 32 is just equal to 5. Let's look now and see, well, what is log base 2 of 4 plus log base 2 of 8 equal to? Well, I know 2 squared is equal to 2. 2 to the 3 is equal to 8. So log base 2 of 8 is equal to 3. And so log base 2 of 4 plus log base 2 of 8 is equal to 5, which is what we wanted. So we've shown that at least for this example it's true, and I'm going to tell you this will work no matter what numbers you plug in for A and B. So now let's look and see what happens if I have division inside of the log. So if I look at log base 2 of x over 4, I'm going to compare this to the graph of log base 2 of x. So it's the same graph that we've been doing multiple times already. I notice now that my entire graph, instead of moving up, has moved down. Everything has moved down 2 units. So I could say that log base 2 of x over 4 is the same thing as y equals log base 2 of x, and then subtracting a 2. If I look at log base 2 of x over 8, I'm going to have the same kind of thing. I'm going to look at log base 2 of x. Look at that graph. Everything on the graph has been moved down 3. So I could rewrite the equation as y equals log base 2 of x minus 3. We have the same relationship between this vertical shift and the original numbers in my function. So I could say, well, y equals log base 2 of x minus 2 is just y equals log base 2 of x minus log base 2 of 4. And then I could also say that y equals log base 2 of x minus 3 is the same as y equals log base 2 of x minus log base 2 of 8. So all I did right here is I rewrote the 3 as log base 2 of 8. I rewrote the 2 as log base 2 of 4. So this leads us to what is called the quotient rule. So the quotient rule tells me, I'm going to put this right here. that if I am subtracting, or not subtracting, if I'm dividing in a log, I can rewrite that as 2 logs that are subtracted. So that is my quotient rule. And then I could go and plug numbers in for A and B and show that it still works. I'm not going to take the time to do that right now. The next thing I'm going to look at is what is called the power rule. So I'm looking at this log base 2 of x to the k, and I want to figure out a way that I can rewrite that. So to help me figure that out, I'm going to look at a simpler case. I'm going to look at log base 2 of x to the 3. This is just the same thing as saying log base 2 of x times x times x, because exponents are repeated multiplication. My product rule tells me that I can rewrite this as log base 2 of x plus log base 2 of x plus log base 2 of x. This now is just repeated addition. Repeated addition is multiplication. I have 3 logs, so this is 3 times log base 2 of x. I started with log base 2 of x to the 3. This exponent that I have up here, all I did was bring it down to the front. So my power rule says that if I have log of x with an exponent, I can rewrite that as the exponent in front of the log. So today we've come up with 3 different properties for logarithms. We had the product rule. I'm going to go ahead and rewrite this without base 2. I'm going to do it so it'll be with any base. So I'm going to say log base b of x times y. This is the same thing as log base b of x plus log base b of y. I had the quotient rule. Once again, I'm going to rewrite this with a base b, so to show this will work for any base. If I have a fraction or division inside of a log, I can rewrite that as 2 logs that are subtracted. And then my final rule that we had was the power rule. That said, if I had log base b of x to the k, I can take that k, bring it down to the front, and it's k times log base b of x. We also came up, or we saw at the beginning, that if I have addition inside of a log, this is not the same as distributing that log. I cannot distribute a log. So I never want to see a log that you're distributing over addition. There is no rule for addition inside of a log.